Thank you.
Good morning, everyone. So today let's start the first talk of this morning, second day of the workshop. And we have Matthew Reece, who will be talking about large field ranges, UV cutoffs, and photon masses.
Thank you. Okay, so I'm going to talk about a few topics that come from papers that I wrote with Ben Heidenreich and Tom Rudelius, and also a paper I recently wrote just by myself. These topics are all kind of closely related to the early Swampland conjectures, in particular the Swampland distance conjecture and the weak gravity conjecture. So I'm going to have very little to say about the more recent conjectures like de Sitter space, although I will briefly say a couple of things about cosmology toward the end of the talk. But the things I want to discuss are largely related to trying to bring first trying to bring these two conjectures, the distance conjecture and the weak gravity conjecture, closer together in some ways, and second, to bringing them closer to having useful applications to phenomenology and to real-world particle physics. So I probably don't need to tell you the details of what these conjectures are because there's been a lot of discussion in the last couple of days. I would say that what we've kind of realized over the last few years is that the Swampland distance conjecture and the weak gravity conjecture are probably sort of two aspects of the same thing. In particular, the weak gravity conjecture told us there's some sort of cutoff at an energy scale given by the gauge coupling times the Planck scale. But what we've come to realize is that all the examples that we have in string theory, at least, and these things are also motivated by internal consistency kinds of arguments, have a stronger form of the weak gravity conjecture that we call the sublattice conjecture. There's a closely related idea that Gary mentioned yesterday called the tower conjecture. And so somehow it seems that the version of the weak gravity conjecture that's actually true in the quantum gravity theories that we know involves an infinite number of charged particles, each of which obey the original weak gravity conjecture bound. And they have different charges. For non-Abelian groups, you'll find particles in different representations, but you always find an infinite tower of such particles. Now, the existence of a tower carries an important implication, which is a low ultraviolet cutoff, because you have many particles, these particles can all run in loops, and so necessarily any kind of process you consider is going to interact with many particles, and the higher in energy you go, the more of the particles in the tower it's going to see, and so you get a low ultraviolet cutoff. And kind of the theme of this talk is going to be that those ultraviolet cutoffs can be very interesting. They can both shed light possibly on how we should think about these conjectures themselves, and they can also be very powerful for making arguments about phenomenology. So the particular viewpoint that Ben and Tom and I have been taking on these cutoffs is that it seems like if we make an assumption that there's kind of a universal scale in quantum gravity where everything becomes strongly coupled, so graviton scattering, photon scattering, any sort of process that you consider becomes strongly coupled at the same energy scale, making that assumption seems to imply a lot of the details of various Swampland conjectures. Okay, so I've mentioned that towers of particles lead to a cutoff. One of the easiest ways of understanding how that happens is through what's called the species bound. And this has already come up a couple of times in talks yesterday. But the species bound is just the idea that if we have many different particles, they all couple to gravity. And so if I compute a graviton propagator, these many particles run in the loop, and they give me corrections to the Einstein-Hilbert term proportional to the number of particles running in the loop. And if we cut off this loop at some cutoff scale, lambda quantum gravity, then when there are many degrees of freedom, the Planck scale is going to be a lot bigger than lambda quantum gravity. So this is a perturbative argument. There are other arguments for this based on black hole physics. There are lots of examples, and the easiest one is just to think about extra dimensions. So if you have extra dimensions that are large compared to the fundamental Planck scale, you know the lower dimensional Planck scale is effectively much higher than the fundamental higher dimensional Planck scale. And that scaling works in exactly this way. Now, one thing I want to mention, there was some discussion yesterday of the Dine-Seiberg problem and the fact that when you go large distances in field space, you tend to find potentials that are kind of exponentially falling. And there were some nice arguments that, that Cameron and Aaron mentioned related to entropy and de Sitter space. I want to just mention a slightly different point of view on that, which I think is maybe a little less crisp and precise than what we heard yesterday, but which comes directly from thinking about these cutoffs, which is just that if you have the Swampland distance kind of behavior where you have a tower of particles becoming exponentially light, then when you go some large distance d in field space, you get an exponentially large number of particles below the cutoff, which is growing as you move farther in field space. And as a result, this species-bound cutoff is actually exponentially falling. And we can generically say that whatever the potential is, if it even makes sense to talk about a potential at all, it should be bounded in some way by the cutoff. As we send the cutoff to 0, the potential energy should also be going to 0. And one way to bound that is to say this should be smaller than something like whatever that cutoff is squared times m Planck squared, because that would source curvatures of order the cutoff. And if we had energies bigger than that, it would source curvatures that we can't consistently talk about in the effective theory. But because the cutoff is exponentially falling, this suggests that the potentials are bounded above by something kind of exponentially decreasing. Really, I should say the absolute value of the potential is bounded above by something exponentially decreasing. So there's a good reason, given the way these cutoffs behave, for potentials to go to 0 at the boundaries of moduli space. But more than that, we could say that if we had a natural theory, we actually expect that cutoff to tell us something about the size of the potential. We just start computing loops, and they get cut off. And there might be SUSY that prevents this from being lambda to the 4th. But in that case, these potentials are always kind of exponentially falling. So this bound doesn't really tell you what we were hearing yesterday, because you could have a potential that's actually much smaller than this exponential, and in fact, we know cases where the potential is just 0. But in non-supersymmetric settings, we tend to have potentials that behave in this way, and so I think that gives us at least some effective field theory reasoning for why, in the presence of these towers of particles, we expect to have this kind of exponential behavior near the boundaries of field space. Of course, that doesn't tell you what happens deep in the interior of field space, so you can't derive the de Sitter conjecture from this. But it's showing you that these UV cutoffs are kind of correlated with things we're familiar with in a lot of examples. Now, what Ben and Tom and I realized last year is that these UV cutoffs from the species bound are correlated in an interesting way with the weak gravity conjecture, and in particular with the lattice weak gravity conjecture. So in particular, let's talk about a U1 gauge theory in 4 dimensions, to be concrete. What the lattice weak gravity conjecture leads us to expect is a particle of charge 1 below the scale e times m Planck, a particle of charge 2 below the scale 2e times m Planck, and so on. And if you have such a tower that kind of saturates this bound, then you can just count the number of particles below some energy scale, and it's given by that energy scale divided by e times m Planck. And you can plug that into the species bound and solve for the cutoff scale, and what you find is the cutoff scale is bounded by coupling to the 1/3 times m Planck. So remember, the original magnetic weak gravity conjecture told us there's a cutoff at e times m Planck, but that cutoff can be a sort of mild form. That can be the appearance of a tower of states. And you can still do field theory as long as you keep track of these states, right? If we see a Kaluza-Klein scale, we can go above it and do field theory in higher dimensions, and that's perfectly consistent. But this cutoff is a stronger sort of cutoff where gravity itself becomes strongly coupled, and local quantum field theory breaks down entirely. So we're claiming that any U1 gauge theory will have a cutoff at this scale. And that's already of kind of mild phenomenological interest. So for instance, there's a very strong bound on B minus L gauge bosons. We know that if a massless B minus L gauge boson exists in our universe, its coupling is bounded above by 10 to the minus 24. What that means is that if such a boson were discovered, we would immediately know that if these conjectures are true, the fundamental cutoff in our universe is below 10 to the 10 GeV. And so conventional gut physics, conventional neutrino seesaws, lots of inflation models just wouldn't make any sense. So, of course, I think it's not very likely that we'll find a B minus L gauge boson with such a tiny coupling. But if we did, it shows you that this conjecture has some utility. But more interestingly, there's another way to calculate a cutoff in this theory, which is to think not about renormalizing the graviton propagator, but to think about renormalizing the photon propagator. So we have these many charged particles. They couple to photons proportional to their charge. And so as we move up this tower, we're going to eventually hit a Landau pole because we keep renormalizing the strength of the electric interaction. And you can ask, at what scale do we hit a Landau pole? So let's assume the UV coupling is big. That's what I mean by a Landau pole. And we have some infrared coupling E. And we want to know how far up the tower do we go before we hit strong coupling. And the answer is you go up to a charge capital Q, which is given by e to the minus 2/3. But in fact, that means exactly that your cutoff is at e to the 1/3 times m pole. So the thing you infer from the species bound and the thing you infer from the Landau pole are actually the same cutoff for a tower of particles that saturates the lattice weak gravity conjecture. So there's something non-trivial about these kinds of lattices of particles that obey the weak gravity conjecture. When you have them, these two different notions of cutoff happen to coincide. And in fact, this coincidence of cutoff scales is not just an artifact of this particular spectrum that I wrote down. It extends to very general settings, and that's what we showed in our paper last year. So let me give you just one kind of quick summary of another example. If I have an SU2 gauge theory, what the lattice weak gravity conjecture tells me to expect is that I have representations of different spins that are bounded in terms of the spin times the coupling times m Planck. Okay, so compared to the U1 case, I now have a lot more particles. I have a spin 1 representation, which contains 3 particles, a spin 2 representation with 5. Maybe I also have half integers, but I just wrote down the integers here for simplicity. So I go up the tower and I find more and more states, and that means both my species-bound cutoff and my Landau pole cutoff are going to behave differently, and we can compute how they both behave. In the species-bound case, we now get the square root of the coupling instead of the 1/3 power. So for a given coupling, you hit the cutoff faster for a non-abelian group because you have more particles and larger charges. And I should say that here I've assumed that what the weak gravity conjecture should mean for non-abelian groups is that we find different representations as we move up the ladder. And there are some reasons to think that's true. It seems to be what follows from the modular invariance arguments in the world sheet theory. But you could have imagined it meant something different, which was just about counting the charges under the Cartan sublattice, and you might be able to sort of leave out some representations by making bigger representations lighter. So what we're claiming is the right version of the weak gravity conjecture is the picture on the left, not the picture on the right. Given that, the same coincidence works out. We calculate the species-bound scale. We can also calculate where does the gauge coupling become strong. And there's another calculation here. You need to know the Dynkin index of the representation. You plug it in, and you again get a cutoff at g to the 1/2 times m Planck. Okay, so that's 2 examples, but in fact this works for arbitrary gauge groups, arbitrary products. If you have a tower that saturates the weak gravity bound, you find gravity has a cutoff, gauge theory has a cutoff, and they are at the same scale. So that suggests that there's something interesting here, where somehow what these lattice or tower versions of the weak gravity conjecture are capturing is that there's some scale in quantum gravity theories where everything is strongly coupled. And if you find a theory with a weak coupling, somehow the way you got that weak coupling was by integrating out a bunch of stuff. So weak couplings kind of emerge by integrating out towers of fields. And they all emerge from some kind of common strongly coupled scale. Now, there are also converses to these statements. If I just suppose that gauge theory becomes strongly coupled at a scale below where gravity becomes strongly coupled, I can already infer from that there must be at least one particle whose mass is less than its charge. In fact, I can infer something even stronger, which is that the average charge of the particles below the cutoff of the gauge theory is bigger than their mass. In fact, is bigger than the cutoff scale itself. So there's some kind of tight link between this idea of UV cutoffs and the weak gravity conjecture, or at least the lattice or tower versions of the weak gravity conjecture. I should say one question that came up, I think, after Rene's talk yesterday was what happens in other examples of weak coupling, like weak string coupling, for instance. And these arguments are a little harder to make in that case because if you send the string coupling to 0 in 10D string theory, you do get a tower that becomes light. It's all the string states. But you shouldn't sort of treat loops of those things in the same way you treat loops of weakly coupled fields, because as you move up the string tower, you're getting sort of extended objects. And so I don't quite know how these arguments work in that case. But there might be a version of the arguments that still works. And let me kind of indulge in a little bit of wild speculation in one slide. I think we've had a lot of speculation at this meeting already on various things, so a little bit more might not hurt. One way you might imagine taking these kind of fuzzy arguments that I'm telling you and sharpen them would be if there's a statement in conformal field theories where you could really prove some kind of sum rule that tells you that the central charge, which is basically the analog of the Planck scale that I've been talking about, is just counting all the single trace operators below some dimension, which is the analog of the quantum gravity cutoff that I've been talking about. And to cover cases like these cases with extended strings, you would want to somehow have a rule that told you how to deal with the case where these things are above that scale, which would be like the stringy states. And so what you would want to do is probably still count them, but maybe with some sort of weight that's exponentially suppressed. So if it was possible to derive a sum rule like that, and an analogous sum rule for the two-point function of the current, then you could maybe take all of these arguments we're making, which are, I think, suggestive but a little bit fuzzy, and maybe make them into rigorous arguments about quantum gravity and ADS. So this is wild speculation. I have no idea how to prove such a sum rule, but maybe people who know more than I do about conformal field theories might have thoughts about that. Okay, let me mention some applications of these UV cutoffs to phenomenology. Interesting applications are going to come from theories that have small couplings, and ideally non-abelian gauge theories, since we get more states in the towers in those cases. So you can go fishing around in the literature for where have people tried to do useful things with weakly coupled non-abelian gauge theories. And there's a nice recent example. There are tensions in cosmological data that can be improved by assuming that dark matter has some non-abelian gauge interaction. So there are light non-abelian gauge fields that mediate interactions between dark matter particles. And what Buenabad and collaborators showed is that if you have a coupling of 10 to the minus 4, you can improve fits by 3 sigma. Well, what we've said is that if you have a gauge coupling of 10 to the minus 4, you should have a cutoff that in an SU2 theory goes like the square root of that number times m Planck, so a cutoff below the gut scale. In a higher SUN theory, the cutoff becomes even lower, and so here's a plot as a function of gauge coupling and n for an SUN gauge theory. The contours here are various energy scales you might be interested in. This is the gut scale. These curves labeled by R are values of the Hubble constant corresponding to a given tensor to scalar ratio you might measure. And this is some scale you might associate with right-handed neutrino masses. And these contours are kind of the maximum energy you're allowed to talk about given our cutoff for a given G and a given N. And the dashed line here is the kind of coupling that they want. And so you can see that kind of coupling for most values of N is incompatible with observable tensor to scalar ratios, although actually not for SU2. So there's still a little bit of room for that kind of theory to be compatible with observable tensor to scalar ratios. There's another theory called chromonatural inflation. It's a particular theory of inflation. I'll say a little bit more about it later in the talk. But they want a coupling of something like 10 to the minus 6. And so you can see that really implies a pretty low cutoff. It's, again, incompatible with gut physics, incompatible with these tensor to scalar ratios. More importantly, it's incompatible with a scale that actually shows up in their own model, or at least marginally incompatible. So this is kind of borderline. This theory is almost ruled out by these UV cutoffs. So what this suggests is that these kind of UV cutoffs can actually be useful for saying things about models that people are proposing, especially in the context of early universe cosmology, or of solving some tensions in cosmological data. And there are likely to be other applications, so I think it's interesting to think about. One thing I want to just briefly mention, because Irene talked about this yesterday, is you can apply a similar logic to thinking about the couplings of the moduli fields themselves. And so if you have a modulus and there's some point in its field space where a tower of particles is becoming massless, You can go near that point and calculate loops of all those particles coupling to the modulus. And those renormalize the kinetic term of the modulus in a similar way that we were talking about the graviton and gauge field propagators. And so you can ask just kind of self-consistently, what should this kinetic term look like if we want the modulus to become strongly coupled at the same energy scale that gravity becomes strongly coupled? So again, taking this idea that there's some sort of universal UV cutoff and everything emerges from that by integrating out towers of fields, you find this weakly coupled modulus emerges from integrating out the tower in a consistent way if the kinetic term goes like 1 over the modulus squared. So in other words, if the distance in field space is logarithmic as a function of this modulus, when the particle masses are sort of scaling to 0 linearly with the modulus. So in other words, as a function of distance in field space, the particle masses are behaving exponentially. And so this is exactly what Uguri and Vafa had told us should happen. But here we haven't conjectured this exponential behavior. We've seen it as an output of a different assumption, which is the assumption that these loops are driving everything to strong coupling at the same scale. Another thing you can work out along these lines is you can apply a similar argument to something like an axion, where you're not necessarily assuming that a tower becomes light at a particular point, because this is an axion, maybe it has a compact field space, I don't ever go infinitely far. But let me still assume that it couples to some tower of states, their masses are sensitive to the value of the axion, and I want the axion to become strongly coupled at the same scale. So if I make that argument, what I find is the average change in mass when I move the axion over some distance in field space is given by that distance over m Planck times the quantum gravity cutoff. And so if I move a Planckian distance, the average particle mass is changing by an amount of order the cutoff. And so I think this is very suggestive. It means that if you believe this picture where everything is becoming strongly coupled at the same kind of scale, you should be very careful about trusting field ranges that are super Planckian. Because within effective field theory, this is really dangerous because the average particle mass is actually moving by an amount that takes it in or out of your effective theory as you're going this super Planckian distance. So that supports these ideas that we should be careful about super Planckian field ranges. Of course, there are various loopholes. All of these things refer to the geodesic distance in field space, and as Arthur and Gary and collaborators have told us, for example, there are examples where the geodesic distance can be super Planckian, but the geodesic distance can be sub-Planckian, but inflation might steer you along some other direction that's super Planckian, and so you might get interesting super Planckian field ranges that are relevant for observations without a geodesic distance being super Planckian. So, so there's no sharp no-go theorem here, but at least there's kind of a caution that you should be careful. Okay. How much time do I have left? Okay. So more recently, I've been thinking about another phenomenological application of these kinds of ideas, which is to photon masses. In effective quantum field theory, we can just add a mass to an abelian gauge boson and nothing bad happens. We don't have gauge symmetry anymore, we have an extra degree of freedom, but that degree of freedom is very weakly coupled if the mass is small, and so it seems harmless. And you can think of such masses as Stückelberg masses, where you sort of introduce a fictitious gauge symmetry by having a scalar that shifts when you do a gauge transformation. And we know that these Stückelberg masses show up all over the place in string theory. But if you look at the way that they show up, they tend to show up in a particular form. And so, so you can go to, for instance, the string phenomenology textbook by Reece and Angel, and you will find lots of examples of Stückelberg masses in string theory, and they tend to look like this. They have Kähler potentials that are logarithmic functions of some chiral superfield, which shifts when you do a gauge transformation. And so SUSY means that this goldstone that got eaten by the gauge field has a radial partner. So that looks kind of like a Higgs mode, but it's not really a Higgs boson. In particular, there's no point in field space where the photon mass actually goes to 0 when you have this kind of kinetic term. And so what happens when you have a Stückelberg mass is the limit you want to take to get to 0 photon mass is actually at infinite field range, logarithmically infinite in the same kind of way we've been seeing over and over. And unlike the Higgs mechanism, that point where the photon mass goes to 0 just isn't part of your field space. And so if we take this to be what we mean by Stückelberg masses, this is the real kind of invariant distinction between Stückelberg masses and the Higgs mechanism, then the Swampland distance conjecture suggests that if you try to send a Stückelberg mass to 0, you should bring a tower of modes light, and that should lead to a UV cutoff. And in fact, we can be a bit more precise about this. We can dualize the scalar that got eaten by the gauge field to a 2-form and apply the weak gravity conjecture to that 2-form. And what that tells us is there should be strings that are charged under the 2-form gauge field whose tension is bounded by the 2-form gauge field's coupling F and the Planck scale. And the distinction between Stückelberg and Higgs is that these are fundamental strings. So in the Abelian Higgs model, we know that there are cosmic strings. The field theta kind of winds around the string, but the Higgs mode goes to 0 in the core of the string. And so these are strings, but they're strings you can describe within low energy effective field theory. They don't tell you anything deep about the UV completion. They're just part of your effective theory. But when you have a Stückelberg mass, you will find such strings. But the distinction is the core of the string now is not just where some Higgs field goes to 0, because the Higgs can't actually go to 0 in the Stückelberg context. There's no such point in field space. And so when you look at examples, these are always fundamental strings. I don't really mean F strings, but I mean they're F strings or they're D strings or they're D branes wrapped on some cycle. They're something that knows about the ultraviolet physics of the theory in a way that these kind of semi-classical low energy effective field theory strings don't. And so we should interpret the tension of these strings as some kind of upper bound on the cutoff of the theory. And if you do that, you would conclude that any attempt to make a small photon mass is going to run into tension with the weak gravity conjecture one way or the other. The photon mass is a product of a gauge coupling and a dimensional scale F. If you make the gauge coupling small, the gauge field is weakly coupled, and that's a problem. If you make F small, the B field is weakly coupled, and that's a problem. And either way, you have a UV cutoff, which is either given by the string tension or the kind of cutoff on U1 gauge theories that I told you about at the beginning of the talk. And so you can just plot what this looks like as a function of gauge coupling and photon mass. And you see, for instance, if you want your cutoff to be above a TeV, and you want to have a very light photon, you need to have really tiny gauge couplings. And this is relevant both for the standard model photon and for dark photons. For the standard model photon, there are kinematic bounds on the mass that tell us it has to be extremely light if it's massive. If you plug that into these bounds, you find the quantum gravity cutoff would have to be below 10 MeV. Well, we know the quantum gravity cutoff in our universe is certainly not below 10 MeV, and so you conclude that the photon must be massless. Now, there's a loophole here, and it's an annoying loophole that I don't quite know how to close, which is we could just be wrong about the unit of charge. We say the standard model U1 coupling is something like 0.3. But what if it's 10 to the minus 15 and the charge on the electron is just 10 to the 15? Then the number E that shows up in this bound is very different. And this is kind of ridiculous. I suspect that there are other kind of swamplandy reasons why we can't have a fundamental particle with charge 10 to the 15 that's light. But again, I don't know a sharp argument along those lines. So there's a loophole with Miller charged particles, which is logically consistent, but not very appealing. Okay, now in the last few minutes, I want to just briefly say a couple of other things. I'm just going to kind of gesture at things because I don't have time to explain them. But if you want to follow the line of these de Sitter swampland conjectures, then there's a tension with slow roll inflation. And there might be ways out that are very different from conventional inflation, like string gas cosmology. But there are also models that are close to slow roll inflation, but that have some extra dissipation beyond Hubble friction. So you can inflate in steep potentials by coupling an axion to some gauge fields in a particular way. This leads some modes to be tachyonic. The inflaton starts producing particles, and that's an extra friction, and it slows down the inflaton. So there are models that do this, models of Enber and Sorbo. There's kind of a somewhat related model called chromonatural inflation that I mentioned earlier. What I want to point out, and this is explained in more detail in a paper I wrote with Pratik Agrawal and Gigi Fan a couple of months ago, is just that these models require a big coupling here, but that coupling is always really a loop factor times some integer. And in chromonatural inflation, for instance, this coupling is tiny. It's 10 to the minus 6. So the authors of those models originally claimed we have an unpleasant large number we put in the model, which is 100 or 1,000. But if you look at the details, they're really putting in an integer, which is like 10 to the 15. And so, so you should be concerned about whether these things have UV completions. And what we showed is one way you might try to explain that large number doesn't actually work with clockwork. So there's kind of, again, an interesting, maybe swamplandy kind of question here of can you get this huge integer to show up in a consistent way in a UV complete theory? Okay. I don't have time to talk about this. I was going to mention that you can use similar couplings to actually populate dark photon, dark matter. But let me just conclude here. We've been exploring the weak gravity conjecture and the Swampland distance conjecture and how they fit together with these ideas about towers of particles. These things imply UV cutoffs. And I think these UV cutoffs lead to some of the kind of cleanest statements about phenomenological applications for these conjectures. Thanks.
Comment concerning Stückelberg masses in stream models, you don't really need to have this minus log behavior. In fact, there are plenty of U1s which get the Stückelberg masses and the color potential is different. For example, difference in singularities. Actually, you have a quadratic term which is axion, well, field plus field star plus the gauge squared. So the log is not vital. What is important is that the mass of the gauge boson is always EF. So the only way to make it light is either E small or F small. And that's going to happen also in these localized models.
Good.
So it applies, but
thanks.
The log form is not crucial.
Okay, thanks.
Just a comment. I don't know if you are familiar, but historically, when Landau discovered the Landau pole in the 30s, one of the first things that he did is to introduce a species in order to see how the Landau pole changes with a species.
I didn't know that.
This was, he realized immediately when you introduce a species, okay, of course, the Landau pole goes into a smaller energy. Now, I understand that your point is that the weak gravity conjecture for you provides the following claim, that gravity always protects the Landau pole. In other words, if you introduce a species, as Landau already realized, then you get the Landau pole at lower energies. But then you say, oh, gravity must protect also this Landau pole. That's the reason you use the species scale. And gravity should be always protecting this Landau pole. You can never go to the Landau pole without meeting gravity before. This is what you are saying?
Yeah, that's a good way of phrasing it. Right. So the gravitational cutoff is always appearing.
Gravity is always before Landau. You'll get Landau pole.
We're finding that they're kind of parametrically the same place, but yeah.
I see. Okay.